Hello everyone, I'm Fangcheng Qiu. I come from Zhejiang University. Today, I'm glad to share our work, JITO, a tool for just-in-time defect identification and localization. Just-in-time means that our tool can identify defects at check-in time. It helps developers save time in finding and locating suspicious defect program elements. JITO can be used just after developers submitting a new change commit. First, JITO can identify if a new change is buggy. Second, it can locate suspicious buggy code lines in the identified buggy changes. Now, introduce the framework of our tool. There are two phases. The first phase is model building. In this phase, we leverage our ESEC algorithm to extract buggy changes and clean changes from the local Git repository. Then, use 40 change features from all changes to build a class file as Defect identification model. It can identify buggy change. Besides, we build a clean line set. It contains all code lines in clean changes, and the lines are not fixed in buggy changes. Then, train an algorithm model based on this set to achieve Defect localization model. The second phase is model application. In this phase, when submitting a new change commit to the local Git repository, the identification model will identify it as buggy change or clean change. If it is identified as buggy, the localization model will find the most likely buggy code lines. Now, let's talk about JITO's usage. During the first time option, we need to set properties and do some preparations. These steps can be omitted in the later use. In IDEA, we choose Tools, JITO, and press Set Properties button. Then set Python interpreter path and the JITO identification path. Highlighted RITO, train set start time, train set end time. Then we can press the Build Model button to build the defect identification and localization models. This process will be performed in the background. We can check status in the status bar below. During this period, we can use IDE normally. If the models are built successfully, it will send out a reminder to us. After submitting a new change to the local Git repository, we can press the Analyze Change button. It will take a little while. If JITO predicts a buggy code lines, it will remind us that the change is buggy and highlighted the suspicious buggy code lines in IDE. Else, it will inform us the change is clean. When we finish the inspection, we can press the Unhighlight button to remove highlights in IDE. In experiment, we choose radon gas and PMD as baseline. We use identification RITO, which is the record of defect identification, and misidentification RITO, which is the false positive of RITO of defect identification to evaluate defect identification phase. Besides, we use MRR, MAP, and top key accuracy to evaluate defect localization phase. Our experiment is carried out under Intel i9 CPU, 16 GB RAM, and Windows 10. In defect identification phase, JITO achieves an average identification rate of 0.843 and a missed identification rate of 0.284. It reaches a reasonable performance. In defect localization phase, JITO achieves MRR of 0.396 in the identified buggy and 0.441 in all buggy. JITO achieves maps of 0.353 in identified bugging and 0.403 in all bugging. It also performs to 2 baseline in all 14 projects in terms of MR and MAP. And JITO achieves top 1 accuracy of 0.265 and top 5 accuracy of 0.544. It outperforms 2 baseline in most cases in terms of top key accuracy. In efficiency, JITO achieves short model building and model application times in small-sized and medium-sized projects, and an acceptable time in large projects. Thanks for your attention.